Whatever works for you, you know. Hello. Um, I hope my microphone is working. Yeah. So, welcome to our. I really don't know which one by order is, but Arthur Olney Williams Jr. talk and lecture, and I will have to explain who Arthur is. But before that, I really want to say that we are honored today to have Gregory Gabadadze, I did ask for the name reading, who is a professor of physics at New York University, now Dean of Sciences, Arts and Sciences, I guess, officially. Just Sciences, yeah, at NYU. And he's also a vice president or vice chair of Simons Foundation, very accomplished and famous, as I will tell you later, a cosmologist, for those of you who know better than I do, right? Actually, Stefan will help me because with this introduction. But before that, I just want to tell you, I'm going to read this story about Arthur Olney Williams, who honors this special lecture, that he's actually a descendant of two very prominent Rhode Island family, Williams, that dates back from colonial founders, Roger Williams, the most famous figure in our state, right? And Olney Will and Olney Street, you know, that the other one. When he grew up in East Providence, and why he got kind of noticed was that there was a national competition for the brightest boy in America in 1930. Yeah, and apparently if you win this contest, then you go to New Jersey in Menlo Park, where Edison himself would actually, you know, congratulate you. The light bulb Edison, right? And so he actually ended up winning this contest from Rhode Island and winning a scholarship, paid scholarship to MIT. And then apparently in our department for a long time, we had a picture of Arthur Williams with Edison. He was 17 at the time, and Edison 83, you know, giving him this award. And he graduated in 1934 from MIT, came back to Brown to do his PhD, and that was right at the time where we only had one professor, actually, Sir Lindsay, and he worked on atomic wave function calculations. He, in 1937, apparently graduated with his PhD, and it wasn't a great year for jobs, so the only place where he could find employment was apparently University of Maine. But a couple of years back, he got back to Brown, and he started working again with his advisor Lindsay on theoretical acoustics, and Art was pulled in to work. And I was also told that this was really horrible time to be a professor in physics. There were no government contracts, and the whole budget of the department, there were two faculty members, Carl Miller and Henry Farnsworth, and it was $1,000 at the time. That's all they had to do everything, okay? And anyway, so Arthur actually, 1952 to 53, Art spent a year in ONR, London, and he returned here to Brown. And I think that he became a prominent professor in our department. I think that Lindsay, his advisor, became a dean of the graduate school. So I guess, you know, moved up, and Art hung out at Brown, and soon was appointed the chair of three-man committee to run the department. So I guess we had a committee back then. In 1955, again, in 1955, he was finally made chair, and I think he was probably one of the first ones where a single person chaired the department. Anyway, over the next years, he really overseen the expansion of the department with appointment in acoustics. This is, I guess, what brought and really decided to build a department in high energy and solid state physics. That was a priority. And I will read very famous people who were hired during Morsley, Bray, Quinn, Feldman, Lanoux, Shapiro, and others. And anyway, so without further ado, I will I just want to say that Arthur worked on problems on underwater sound and was awarded a Pioneer of Underwater Acoustics Medal in the Acoustic Society of America in 1982. Somewhere in the 60s, he became a Ford Hazard Professor of Physics at Brown. So anyway, now let's go to our guest. And I see that Greg actually he got his master's degree at Moscow State University, a bachelor award in Tbilisi in Georgia. And Greg got his PhD in Rutgers University in New Jersey, and after that went for his first postdoc to NYU, then there was CERN, and then came back as a faculty to NYU. And I would like my colleague Stefan now to tell us about all this great accomplishment that Greg there are 2 theory models which I found out in cosmology that carry your name, and that was even before you became a professor, right? So.
Yeah, well, first of all, it's a great honor. I guess, since I'm the chair of the colloquium committee, it's fitting for me to, coincidentally, so some of you who know I've told a story about Professor Dean Gabadadze that I'm not going to tell now, but that story left him as a hero of mine, because when I was a young postdoc, he was a more advanced postdoc, and he came to Stanford and really showed me how to do it. And, Greg's contributions, it's sort of like, if you think about music, when you're hearing a lot of music, you're hearing maybe jazz music, people are playing a bunch of stuff, but there's always one player whose music clarifies everything else. And the work that you've done over the years have served to be this kind of clarifying guidance for a lot of young theorists. Because while you are a master quantum field theorist and relativist, you've managed to make contributions that kind of give us guidance. Your work, for example, in addressing the cosmological constant problem by the so-called DGP mechanism was basically for many years, held the fort, so to speak, for the field. And then later on, the massive gravity program that you did with Tali and your student postdoc, Claudia Duran, also gave us a lot of guidance in how to really not only think about theories, modified theories of gravity that actually had real signals to go look for, but for those of us like myself, of how to go beyond, sort of the current framework. So yeah, we're very excited. I mean, a lot of Greg's work, even though it can be sometimes very technical, has this clarity in it in terms of it's deeply seated in experiment, and with observations in mind. So thank you, Greg, for being here. We know how busy you are, and it's a real honor to have you for this special lecture.
Thank you, Stefan, very much. Thank you, Vesna. Thanks, everyone, for the invitation. I'm delighted to be here. I'm especially pleased to give this lecture in honor of Professor Williams, who I learned was the person who established first modern physics department at Brown. That's pretty amazing, so I'm very honored. Thank you. I'm going to talk today about the subject which is at the overlap of classical gravitation and combined with quantized fields. And the latter, obviously, is the standard model of particle physics, which is extremely successful theory in describing lots of scattering processes, lots of other phenomena happening in the universe. We have great confidence in it. So there are a couple of loose ends here and there which would like to extend to go beyond the standard model to explain things that are not yet explained by the standard model, such as dark matter, for instance, or the baryon asymmetry on the universe. But short of that, it's an amazing theory. On the other hand, you have theory of gravity, general relativity by Einstein. That's another extremely successful theory. Primarily, we regard it or we use it in the classical context because most of the phenomena that are happening around us don't really require quantization of gravity, but we all deeply believe, or most of us do, that gravity, as any other or three other forces, should also be quantized. It should be some kind of quantum theory. And in principle, there is no conceptual problem to quantize general relativity as an effective field theory at low energies. So you can be thinking phenomena which are at scales a lot smaller than Planck mass, and for that it is just sufficient to have gravitational physics as described by general relativity plus quantized standard model if you need to address something along those lines. Naively, it looks like this combination should be nice and safe, but what I would like to argue today is that there are certain quantum effects which go under the name of trace anomaly or scale anomaly or conformal anomaly. This is three different names for the same thing. Once you incorporate them carefully in that combined theory, there are some difficulties. There are some theoretical complications appearing in that combined theory. And as a result, you probably need to introduce additional particles. So I'll be talking about one approach to that problem, which introduces minimally the minimal number of particles, that with just one new particle. And that's what the talk is about. And then I'll talk about possible observational signatures of that particle. So let me begin with the following question. Among the propagating degrees of freedom, is there a propagating degree of freedom for any standard model fields that we use in the Lagrangian? Of course, there are gauge redundancies, and let's say we remove the gauge redundancies, but then we look at the fields that we ascribe certain physical meaning. And the answer is yes, because we quantize all of them, and those quanta correspond to the particles. You've got photons as a quanta of electromagnetic field. You've got the Higgs particle and the fermions and so on and so forth. So you can ask the same question in the context of general relativity. And the answer is not immediately clear because of the two examples that I will give you on the next slide. And some part of my talk will have something to do with that aspect. So on the one hand, we know that massless spin 2 particle, which is a graviton, has two helicity states. That just doesn't require any Lagrangian description to make that statement. It's a consequence of Lorentz invariance and the representation of that group. And those two states are the ones that you very often see consequences of in the context of gravitational waves, for instance. What that picture shows is a gravitational wave which is incoming to the plane of the screen. And one state will be creating the forces on the ring of particles. So let's say you have a ring with some massive particles, gravitational waves coming in, and you will get distortions this way or this way, depending on the phase. That's one. And the other one will be distorting with 45 degrees with respect to the coordinate system, rectangular coordinate system used there. So combination of these two are the helicity states of a massless graviton, helicity plus and helicity plus minus 2, as we usually call them. And that's it. There is no other physical state or propagating state, I should say, in that theory. Some of the things I'll write on the blackboard for the experts so that they're not bored by more general presentation that I'm doing on the screen. But if you don't necessarily follow these equations, that's okay too. So the story will be on the screen. So if I expanded around flat space, so I could go into what's called ADM decomposition to extract all the physical states. So this is a standard decomposition of fluctuations. The zero component will be a Lagrange multiplier, as you know, and this is the vector part, which has a transverse part, and the longitudinal. Longitudinal, you can choose gauge equals to 0. And the physical states are in here, in the IJ transverse traces components. Those two components, which are denoted there differently with a plus and a cross, they are in here. So these are the physical degrees of freedom of the massless graviton. So these are gauge artifacts, these two. But this one is what's called the conformal mode. And I would like to pay special attention to that mode. Lots of things will be about that particular mode. So it's not dynamical. Yet, if you write the Einstein-Hilbert Lagrangian in this formulas, you would say that those modes entirely disjoint from the vector modes, from the scalar mode. So they have separate dynamics at the linearized approximation for your counting. And in the scalar sector, what you get is this. So that's a scalar part of that Lagrangian. Now, why that is important? That's important because of what we do in cosmology. Thank you. What we do in cosmology is, because of the observational evidence, we assume that the isotropic and homogeneous representation for the universe is a good approximation, and we use what's called the FLRW ansatz, in which the scale factor, which is the same as the conformal mode, plays the dominant role. Here is a standard picture of how our universe is expanding. You can imagine surface of this balloon being our space-time, and the radius of the balloon is actually time. So the universe is expanding, and between objects, let's say physical objects, pick one or two, the distance, physical distance, is growing. According to this law, physical distance is the scale factor times the coordinate distance. Coordinate distance is just this grid. As you see, between these two, let's say there is 3 boxes only, and they stay 3, but the physical distance is growing. So the scale factor describes physics of it. Now, the question then is, why is there a wave corresponding to that scale factor in general relativity? And the answer is that there is none. It's not a particle. You can go ahead and quantize, but it's not going to be a propagating particle. That's already seen in this expression. So you have something which looks like kinetic. Actually, it is kinetic term. This tau dot square, that's a kinetic term of somebody. You also have a gradient term. Its coefficient is kind of off. It's not Lorentz invariance, but nevertheless, it's a gradient term. And then you have Lagrange multiplier times Laplacian of tau, which enforces that this tau cannot be space-dependent. So in this simple context, even though this part is there, you can only have time-dependent fields, which is not enough to have propagating degree of freedom. We cannot make a wave out of it, but you can do things like this. You can have time dependence of that function, which actually can contribute physics this way. The question is if quantum corrections modify this story that I just told you about. Any questions about this? Okay. So what I'm going to do now is to use the gravitational field as external, although it has dynamics. I keep its kinetic term. There is Einstein-Hilbert term here. It's propagating. As I said, I don't necessarily need to quantize it, but if I needed to, I could. But for simplicity, it's just convenient to think that way. And again, for simplicity, I'm going to take a toy model of the standard model in which there is just one fermion. It doesn't matter. You can add all the standard model particles. The answer will be the same, just for convenience of presenting and for your thinking and following this talk, perhaps. That's the easiest thing to do. So this is the Einstein-Hilbert term. My Planck mass is just m. factor of 2 difference, that's why just m. And then let's say this is a photon. E0 refers to a Bayer coupling constant. F0 again to the Bayer field strengths of electromagnetism. And this is a fermion, Dirac fermion, let's say, again, the Bayer. So we're going to do renormalization, and renormalization is due to interactions, let's say electromagnetic interactions, or U1 interactions in this particular case. Again, it can be most general interactions of the standard model. And you may ask a question, what's the one loop result for the 2-point function, where in the vertices you have the energy momentum tensor, right? If this is a graviton, these wavy lines are gravitons, and the solid line is this fermion. So this would be the energy momentum tensor at the vertex, because that's how gravity couples to matter. So what would be the result for that 2-point correlation function? That's been known for quite some time. The original calculations were done in the mid-70s, where these authors noticed that there is something unusual about that 2-point correlation function. Unusual in terms of conservation properties or the word identities that you would expect that correlation function to satisfy, right? So you expect energy momentum tensor to be conserved. And if this is a scale invariant theory, as it is in this case, for simplicity, you also expect its trace to be 0. And what they've discovered is that once you calculate the loop, those two cannot be preserved at the same time in a diffeomorphism invariant theory. And let's go step by step how that happened, because the details are important here. So they did calculation in dimensional regularization. This is the answer. Dimensional regularization is a tool in which you artificially go from 4 dimensions to 4 minus 2 delta dimensions in this case, which regularizes certain divergences, and you extract those divergences in terms of that parameter delta, and then you renormalize the theory, and that's how you cancel the divergences that are present in the Bayer quantities here. So they've done that calculation at one loop. If you do that and then ask the question, what is the full nonlinear term, which you should introduce a counter term to cancel those divergences, you will find something like this. This is a gamma function, Euler gamma function, and this is integral of some number. A is a coefficient which depends on number of particles, in which case, in this case, I just use one fermion. In general, it will be fermions and all the bosons and so on and so forth. All of them entering with plus sign as long as you are considering conventional representations up to spin, including spin 1. And E stands for some combination of curvature terms. It's called the Euler density. It's Riemann square minus 4 times Ricci tensor square plus just Ricci scalar squared. That's what E is, and you restore that form from the different, from diff invariance of this calculation. So then a result of that is what's called the trace anomaly or scale anomaly or conformal anomaly. And let me pause on that. So in any scale invariant theory, you expect the trace of the energy momentum tensor to be 0. Reason why is because that trace you can equate to the derivative of what's called dilatational current, right? So when you have global symmetries, as you know, as a consequence of those global symmetries, there are conserved currents. That's Noether's first theorem. And in the case of dilatations, there is a conserved current, dilatational current, and conservation of that current implies that the trace of the energy momentum tensor should be 0. But then you discover that as a result of the calculation, then it's not. It equals to this expression. So the trace equals to something which is quadratic in curvatures. This term is also quadratic in curvatures. And they have special names, the A anomaly and the C anomaly, because they have different nature, some of which I will discuss. There is, of course, other parts of the trace of energy momentum tensor which are related to conventional matter. Let's say electrons and the protons, they all have masses. If you were to write the full standard model, you would get here other terms But all of those are known terms due to conventional physics, due to the mass scales in any theory. The point of the scale anomaly is that you get additional terms, which are not there if you just treated your Lagrangian classically and you took, equations of motion when you calculated trace of energy momentum tensors. These are always in addition to the conventional stuff. So this is very similar to axial anomaly. Actually, today when I was talking to the students and the postdocs, in Stefan's group, so we talked a lot about axial anomaly because they happen to be interested in that. And so we emphasize the fact that anomalies always emerge as a clash between at least two symmetries. In the case of the axial anomaly that you might be well familiar with, it's a clash between gauge invariance or global U1 conservation of charge and the axial symmetry. You cannot preserve both together at the quantum level, so you need to give up on one. And because we want charges to be conserved in our theory, because they are in our universe as far as we know, so we give up on conservation of the axial current. So that's a choice in the renormalization procedure, actually. Here, again, there are two symmetries which are in class with one another. One is, diffeomorphisms, and another one is the scale invariance that I talked about. And you cannot preserve scale invariance while you preserve diffeomorphisms, and hence that result. And that paper on previous, actually this paper too, very clearly, I think very clearly understood those things. Now, the next question you may ask is, do I need to calculate all this loop all the time when I treat my physics in the context in which I'm asking these questions? Can I write down some kind of effective Lagrangian which already includes these quantum corrections, which includes this trace anomaly? Such questions are easy to answer in many toy models. For instance, in two-dimensional models in which there are anomalies, you can write, and some of them are exactly solvable. Actually, you can write exactly those low-energy Lagrangians, which exactly capture those quantum anomalies at the classical level, classical in quotation marks, because that's an effective theory which now gives rise to the anomalous equations already by doing variations of your Lagrangian. So you want to do something like this here too, and actually that's the question that was asked first in these papers by Riegert and separately by Fratkin and Zeitlin in '84. So they've derived it their own way, but in a way that I was presenting this, it's also easy to see what that Lagrangian is. So in going back to this answer, so you are in d dimensions now, and you should be very careful about taking this delta goes to zero limit, which is a four-dimensional limit, because there is this gamma function in front. As you can see, this is gamma of delta, which is divergent, but then there are pieces here which are proportional to delta, and when you combine the two, you get finite results which don't depend on delta. Interestingly, axial anomaly also can be understood in those sorts of cancellations of 1 over delta times delta. So they have very similar features in that regard. So that you can do by obviously starting in d dimensions, in which you have to introduce additional fields, because not introducing them would be making certain assumptions. And when you do that and take the limit, indeed, what I described in words happens. So from the integral, there are pieces which are proportional to delta, but because there is 1 over delta in front, they give you finite terms. And these are the finite terms. So it looks scary, it might be, but I'd like to argue that there is some interesting structure here. First of all, this term is that's sigma, the sigma field, times the Euler density. If you shift it by a constant, this is an integral which is an integer. It measures topology of your space. In a conventional Minkowski space, this shift is 0. And here, sigma, as you can see, you can also shift sigma. So this is sigma shift symmetric, this term. Now, this term, if you were to vary with respect to sigma, would always give you only two derivatives of sigma, as you can easily see. But these are less obvious. And typically, you'd be worried about these sorts of terms because they are higher order derivative interactions. So this has two derivatives, and that's multiplied by derivative of the field squared. And it's not obvious at all that this would give you second order differential equation. So danger is that you may have higher order differential equations, in which case the Cauchy problem won't be well posed, or rather you would need to introduce additional data, which means that actually you are describing more particles than you think you are describing in terms of the fields that you've written. But remarkably, this has a remarkable property that once you do variation, you get second order differential equation from this. And from these two. So these are called actually Galileons, if you heard that name. This is called cubic Galileon, this is quartic Galileon, and their special combination like this is called conformal Galileons. What they are is a Nambu-Goldstone boson. This sigma is a Nambu-Goldstone boson of spontaneously broken conformal invariance. And actually, I'll jump to this line and then come back to the other two lines, because what I just said, you may ask the general question. Suppose you want to start with conformal invariant theory. This group is a group of conformal symmetry in 4 dimensions. That group has 15 parameters. And let's say it's broken down to the Poincare, group of Poincare, which is the fundamental symmetry of our world that we, as far as we are aware of. So there is a standard cosset construction that field theory has worked out since the 1960s. You can apply that construction, and you will discover that this very term, exactly the same term, is just the Wess-Zumino term of that cosset construction. So that tells you that it realizes, this sigma realizes nonlinearly the scale invariance. And as I said, these authors constructed it very different, from very different approach. They just asked what's the right structure which would give me the correct anomalies, and they just reconstructed this thing. And the same thing was used in the context of proving what's called the A theorems by these authors. Now, so far so good, but here is a problem. If you are regarding this as effective theory with general relativity, the issue is this, that the sigma field, as you can see, has no kinetic term, because you could have written this sigma kinetic term here with whatever comes out of the construction, but it's absorbed, it can be absorbed by conformal redefinition of the metric, because it's just a conformal mode. So no kinetic term for sigma, but then you do have these nonlinear interactions for sigma. And that's always dangerous. Whenever you see some theory, somebody gives you a theory in which there is a field or a particle which has no kinetic term, but higher order nonlinear interactions, you should be immediately alerted, because that's not a healthy theory. I'll give you many arguments now why it's not a healthy theory. So let's say you introduce some sources, let's say a planet, and in the leading approximation in small field, you solve the Einstein equations. These are all higher corrections. In the leading order, you just get Einstein's equation with conventional solutions. But then you plug that solution into this Lagrangian to find out what the perturbations are about that solution. And from here, you will immediately see that the kinetic term for sigma is, okay, there is one sigma missing here. It should be d mu sigma, d nu sigma. My apologies. So the kinetic term for sigma will be T mu nu, which is the stress tensor of matter, times d mu sigma, d nu sigma. Well, that's completely unacceptable, because depending what source you take, you get different types of instabilities. For instance, for positive curvature space, you get a kinetic term. So you get, let's say, healthy combination, but for another negatively curvature space, you get negative kinetic term as well as a negative gradient term. Or for conventional matter, which positive energy, you get conventional kinetic energy, but opposite sign for the gradient term. It will be it will give you gradient instabilities immediately. So they are either ghosts or tachyons or gradient instabilities. These are three options. None of them are good. And this is, general relativity combined with standard model. The only dependence on what particles I put in is in this A. A has in it all those particles. So another problem, or related to the previous one, is actually the one that I would like to emphasize because it helps then to understand how to solve the problem. And that is that you can start with that original high, dimensional regularization action, and you can look at scattering amplitudes, let's say 2 gravitons into 2 gravitons, so that their momenta and polarizations, all of them are in 4-dimensional plane. So this is what it would give rise to for 4-dimensional theory. And that calculation was done if you choose it carefully. And the answer for the amplitude blows up when you take delta goes to 0. And you can ask a question, why this is so. You go back to the similar answer, what I gave you on the last slide as to the source of the problem, that there is an additional degree of freedom here, which previously I called sigma, and I kind of inherit that notation here as well, in front of which kinetic term is delta squared, and there is a finite quartic term for it. If you now rescale this sigma to make this to be 1, then 1 over delta will go into your quarting interaction, and it will give rise to this sort of amplitude precisely. 2 to 2. 2 sigma particles into 2 sigma particles, that's your vertex. So these are, I should have said, these are just standard Mandelstam variables for scattering processes, right? So combination of the momenta. So the amplitude blows up. It's exactly the previous story because there is no kinetic term, but still some higher nonlinear interactions, the amplitude blows up. And that's definitely not acceptable. So that means that theory is sick at every single energy scale. No matter how low you want to take it, it's still problematic. Of course, if you take strong backgrounds, gravitational backgrounds, like I discussed here, you will generate additional kinetic terms. And then you would hope that the strong scale will be determined by the strength of that background. That by itself is strange, but this problem of different signs and different instabilities will persist in that case too. So that cannot be a solution. It's still a problematic theory, even if you'll be insisting on considering this on various types of backgrounds. Okay, so what's the minimal way to solve this problem? And minimal way, I'll give the answer and then I'll explain why, is to postulate that there exists an approximate nonlinearly realized scale symmetry with its own Namu-Goldstone boson. I'm calling it phi. And this is how the action of gravity should be amended by the dynamics of that phi, which would make everything that I told you, all the problems, go away. So phi here is some scale times e to the minus sigma. This would be a new physical scale in the theory, and you will see what its consequences are. But that's the Lagrangian you would need to start with. And if you do so, you go through the steps that I outlined, you're going to get Lagrangian without those problems. Right? Simply speaking, in this theory now, you will have additional kinetic term for sigma here. It's not necessarily obvious from this writing, but you can. It requires some conformal transformations, and then it becomes obvious. So that kinetic term comes with its own scale, this m bar, right? So you can think of this scale as some high energy scale, not yet specified. We will have to look at the observational consequences of this and try to understand what might be the bounds on that scale or what might be the consequences of that scale. But till then, there is some new physical scale. Now, for all of this to be meaningful, this scale has to be a lot smaller than the Planck scale. And the reason why is because this action, in general, has infinite number of corrections. because of quantization of gravity or string theory, for instance. All of them are at string scale or Planck scale. Let me assume they are close to each other. And in order for any of the statements that I'm making to be meaningful, all this sector should be at scales a lot lower than m Planck. So without the new particle, that's certainly the case, because I told you the strong scale of this theory is actually 0. 0 is way below m Planck, for sure. But when I introduce m Planck, when I introduce m bar, I meant to say, that m bar better be way below m Planck for all this discussion to be meaningful, and that's an assumption in it. Okay. Then let's study what happens with this sigma field now. Now sigma field has a kinetic term. You can rescale it appropriately, and everything is all right. All those divergences are removed, except that you still have strongly coupled behavior. Because these operators, which were originally there, which were strongly coupled at 0 scale, now they are coupled at the scale m bar. They didn't disappear. They are there. You may say, fine, I'm going to study physics only below m bar, and there is something is happening m bar. I do not know. But as long as I'm below m bar, that's fine, indeed. But I'm going to tell you that you can do more. In fact, you can resolve this m bar scale given in this framework. So this is one of the examples in which you have strongly coupled theory at some scale, and there is a way to resolve that strong scale and go about that scale. And on the next slide, I will tell you what does it take to do so. So for convenience of thinking, at this point, you can just assume that this m bar is way above 10 TeV and way below m Planck. Yes, please.
Yeah, so could you solve the problem with the kinetic thermal sigma by doing a Weil-Fiber definition of the method?
By what?
Weil.
Yes.
Similar to go from the string twice on purpose.
Yes, so it won't solve that problem because, yes, if you do the Weil redefinition, you still get, in this piece, as you know, you get still Einstein-Hilbert, then you get the sigma kinetic term with wrong sign, with a negative sign, and you get the mixing between them. So it's not solving because any of those amplitudes, when you rediagonalize, you will still get infinitely strongly coupled behavior. And the fact that that cannot solve is already telling you that this kinetic term, if you write down the correct sign for the tensor mode, the conformal mode necessarily has to have negative sign, wrong sign. So actually, this is related to this. This tau, that's why I wrote negative sign. It's also, since you asked me, let me go back. It's very interesting. It's not typically written in textbooks. So when you evolve the universe, right, we write down the Friedmann equation, h squared equals to, let's say, rho divided by 3 times m Planck squared, right? So this is a dot square over a squared, h squared. And you may ask, assuming that this came from some reasonable field theory, let's say scalar field theory or something like this, with conventional healthy signs, you may ask, what is the sign of the kinetic term of this A in the Lagrangian for me to get this equation with the right signs? The answer is that it has to be ghost-like, it has to be a bad sign. Otherwise, you don't get Friedmann equation. You get Friedmann equation with the wrong sign.
Because it's a constraint equals to 0.
That's right. And then you are in worry, as you just said. Wow, is it a ghost? But the point is that there is no propagating degree of freedom. So it works pretty in a subtle way, yes. All right, so what's the completion about that m bar? Turns out you can do it. And I'm just giving you, one slide description of the whole paper, which we wrote with my colleague Massimo Porati from NYU. And if there are questions, by the way, you can stop me at any time. So the answer is that you can think of that sector which resolves this m bar strong scale to be either as a some kind of CFT with spontaneously broken dilatation invariance, or you can have this description of that CFT in terms of the ADS geometry through the ADS CFT duality. And because ADS language is easier, because it's a classical language, you just don't need to appeal to any quantum calculation. You just can solve the partial differential equations, essentially. That's the language that is presented here. So you have ADS space in between of two what's called branes. These are two 3+1 dimensional word volumes. And on one of them, you view the standard model fields to be localized, but the gravity is everywhere. So this goes under the name of the Randall-Sundrum construction. And the other brane is viewed as a cutoff. So one of them is an infrared cutoff, another one is an ultraviolet cutoff of your four-dimensional dual conformal field theory. But you don't necessarily need to pronounce any of these words. You can just solve classical equations here and see how that strong coupling scale gets resolved. So it's pretty remarkable, actually. I didn't really expect that would work, but it does. So what happens is, so there is a new scale in this theory which is related to the distance between these two branes. So that's the mass of the lowest Kaluza-Klein mode. And that scale is below what's analog of m bar. M bar here is number of colors times depth. So that scale is below. So that means that before you resolve that strongly coupled scale, there is lots of particles entering. And it makes sense. In every single time when we've seen in physics resolving some strongly coupled behavior, we have lots of particles entering before you hit that high energy scale. And that's what's happening here. The Kaluza-Kleins organize themselves in a way that strong coupled behavior goes away. And related remarkable thing is that Rigert-Fradkin-Zeidlin action that I talked about, you can just derive from here, from classical equations and integrating out the curvatures of the bulk. And then it kind of rounds that picture very nicely because you explicitly see who this sigma field is. In geometrically, it's just a radion. It's a field which is kind of measures fluctuations of these two branes with respect to one another in fifth dimension. And you can just calculate. You will find out that it's this other brane actually leads to spontaneous breaking of conformal symmetry in the CFT. That was done in earlier work by Zaffaroni, Ratazzi, and others. And then you have entirely consistent description all the way up to the scale of the validity of this theory, which is way above m bar. So what about physical consequences? So I just told you that you have to have that extra scalar. So this is minimal way of avoiding those problems. What about physical consequences? In high energy regime or early universe, that scalar is just massless. It had that, in the new terms that I talked about, it had the Schitt symmetry. But this is still in progress, but we believe that at low energies, actually, it will acquire mass because of the interaction with gluons. So what this scalar couples to is the anomalies. It only couples to trace anomaly. It couples to trace anomaly in terms of the QCD fields. It couples to trace anomaly in terms of U1 or photon fields. So those couplings are just sigma times field strengths of QCD or sigma times field strengths of photons, and that's it. It doesn't have other couplings. It has those nonlinear couplings with gravity and self-couplings that I talked about, but that's it. So from these couplings, you would expect it to modify what we typically call the dynamical scale of strong interactions based on simple observations. This is the conventional kinetic term for the gluons, and this is a very similar term in front of it, you have just that field times the beta function, because this is what gives you the anomaly. So that means that this theory is the old QCD in which 1 over g square you replaced by some effective 1 over g square, which depends on the scalar field. And then you can run every single argument that you know of in QCD. You can run, they go through, except that you have to be using that alpha effective. So this is dynamically generated scale of QCD in terms of that alpha effective. It's a renormalization group invariant, and so on and so. This is a beta function of QCD. But then you can also apply what was worked out long ago by Migdal and Schiffman, that by asking a question, is there a low energy Lagrangian which encodes an infinite number of word identities related to the fact that there is one dynamically generated scale in QCD which has this expression, the expression on the previous slide, because that's a very specific expression, and from that you can get lots of word identities as they've derived, or them and their colleagues derived prior to this paper. This paper just looked at the effective Lagrangian. So if you use those results, you will get that this sigma acquires a mass, which is somewhat similar to how Axion acquires a massive QCD, but there are differences too. So scale-wise, it goes as lambda QCD square over m bar, but then there is a dependence on lambda QCD, but also there is additional dependence on m bar, depending what terms you wrote for that phi term. Because in the phi term, you do have freedom to add one more piece there, which is still conformal invariant. So it depends on that. So if so, then there will be constraints on this which are similar to the Axion constraints with minor differences. Axion couples to GG tilde, and that's color electric field times color magnetic field. This one couples to G squared, that's electric field square, color electric field square, or color magnetic field square. But modulo those differences, and modulo difference in the mass formula, physics is very similar. As you know, on the Axion, the strongest constraints on its coupling constant to matter is due to the cooling rates of stars, in particular the giants. Here, that manifests through the following logic. This was the original coupling, but this coupling, if I take matrix element of this coupling between two nucleon states, for instance, it's going to generate coupling like this, effective coupling like this. Simply because this is a trace of energy momentum tensor of QCD, and its action on the states of two protons is proportional to the mass of the proton. So that's how you get the mass here. So the ratio of nucleon mass and that m bar scale enters as a coupling constant, and then there are constraints on that. And so the processes like this, nucleon scattering, there's a production of sigma, or photon sigma conversion in the electromagnetic fields of a nucleus, or gamma-gamma fusion. These are standard processes, again, used in the Axion physics. They will also be present here, but with slightly different rates. But the orders of magnitude are somewhat similar. So at least in this work, which is still in progress, our preliminary estimates are such that m bar should be somewhere bound in this region. So that's a fine region. It's way below m Planck, so it makes sense to talk about all of these things that I told you about. Now, how about, I know I'm running a little late, but I'll finish soon. How about the cosmology? So about the QCD phase transition in terms of temperatures, this is expected to be almost massless or massless. And first question would be, is there appropriate solution for cosmology? And here is the modified Friedmann equation. This is the conventional part. This is, again, conventional part. It's this part that I wrote here. But the new term looks like this for homogeneous and isotropic universe. And I left out the nonlinear terms, but they all have this combination, actually. So sigma dot equals to h is a solution. That means that the sigma acts as a log of the scale factor, which makes sense because this is a conformal mode. This sigma acts as a conformal mode. So on this solution, it's very explicit. And then you recover standard cosmology. You get all the standard cosmology with great approximation, as long as curvatures are below that m bar. But how about fluctuations? Because these are massless fields in the universe, so you can work it out. It's still work in progress. At this point, what we're finding is that that field by itself wouldn't give you too much because it's conformal. It doesn't sense the FLRW metric too much. Actually, it doesn't sense it at all by itself because it's conformal. It's similar to the vector fields. Vector fields, if you plug in the FLRW metric in their action, that action just is flat space action because it's conformal. Same is happening with the leading terms of these fields, but it mixes with an inflaton. And because of that mixing, you still generate some density perturbations in the early universe. They'll be isocurvature perturbations, but they are small. So at this point, we're finding that those are small corrections. So we are confident to talk about this, but not yet confident to publish it. So hopefully we will publish this soon, and the final answer you will have there as to what the predictions are. So let me finish. What I argued was that consistency of general relativity, when combined with the standard model and taking into consideration the trace anomaly or scale anomaly, is problematic unless there is a new scalar degree of freedom, which effectively is the conformal mode, dynamical conformal mode. That's one way to solve this problem. Well, another way you may say that, well, let me cancel that trace anomaly entirely. That's another option, but that would require introduction of some spin-a-half fields in certain, depending on the, what exactly the coefficients A and C are. You need to introduce certain number of three-half. Did I say one-half? I meant three-half fields, not one-half. Three-half fields to cancel that anomaly. That's another route which I didn't explore. But in terms of the scalar sector, this is the way to solve it. It comes then with some new physical scale and bar. And we don't have to be scared of that, although naively it looks like it's strongly coupled at the M bar, but we have exact theory which resolves that strong coupling and kind of enables you to calculate things about that M bar as long as you're still below Planck scale, at which you would probably need string theory to calculate. But way below that, you are in good shape. So there are observational consequences in the early universe because of the quantum fluctuations during inflation, for instance. That's one example we're thinking right now and calculating. And another one is more like restriction or constraint of that bar because stars would cool faster if you allowed that scalar to be coupled in a significant way to matter. And obviously, the star cooling theories, conventional star cooling theories, are in excellent agreement with observation. So that imposes the bounds on that coupling. And I mentioned on a previous slide as to what those bounds are. So there is still a lot to be uncovered about this and understood, but that's the status as of today. So thank you for your attention. Yeah, it's right there. Yes, no.
Any questions? Well, thank you, Greg, for this wonderful talk. I'll go up there and then. Sorry, issues with the. Yeah, sure.
So thank you for the talk. The M-bar scale, when you wrote down the Einstein coupling and the Galilean Lagrangian, those types of terms are pretty nicely constrained from gravitational wave physics. I would expect that your 10 to the 10, the bound that you had put previously, yeah, this one right here, that's probably consistent with the constraints from LIGO for that term, the G mu nu term.
Yes, so for those terms, the suppression scale is higher than M bar because you see here, there is a combination of, in both of these, in this one and this one, which can give rise to the effects that you are mentioning. So you will get additional powers of M Planck as well. Here you will get 2 powers of M Planck. This would be, the scale will be cubic root of M bar times M Planck squared. That will be the scale. And here will be, again, cubic root of M Planck times M bar squared. But we are aware of those constraints, and in that context are also looking, but so far it seems okay.
Very good, okay. And then the other question is a little bit more fun, maybe. Have you thought about this scalar as being dark matter itself?
Yes. Yes, that's indeed part of this ongoing paper that we are working with David Spergel and Georgi Tukhashvili. So yes, because it's axion-like, lots of axion physics applies here with small changes, and we are definitely looking at misalignment type mechanism or thermal production, although most likely thermal production will be even more suppressed than in the case of axion. We are definitely looking at this. I don't want to say one way or another because we have not finished that calculation, but we are excited for it to be a candidate, if that's realistic.
So precisely for the dark matter, the effect seems to be similar to the axion,
Yes.
competing maybe.
Yes.
But what do you have in mind for black holes? What would it? This would be something different.
Yes, what we wanted to have is if there was an opportunity for large-scale quantum fluctuations in the early universe, which would collapse, which would get enhanced by inflation, but then collapse into black holes.
Right.
That kind of scenario. Okay. So before any large scales are reached, so it won't be in contradiction with any of the CMB story that we know of. So this is still very short scales that we are talking about. So that's what I meant. That's one of the projects in that context of dark matter that we are looking for. Okay. So we can say that we can produce the smaller ones, but they decay before they reach us. If they are, between less than 10 to the 15 grams, I think is the bound. If they are less than that, then they never survive because of the Hawking radiation until now. So the challenge we have is to get heavier ones, and not yet, but soon. We'll see.
Thank you for the talk. So could you repeat in this random syndrome construction, what is the meaning of the sigma? It's like it's a radion. Is the radion you said?
Yeah, it's a radion.
I might be okay. I'm not sure what I'm going to say, but doesn't radions have like runaway potentials?
Okay, so very very good. So in the conventional Randall syndrome picture, there is what's called the Goldberger-Weiss stabilization mechanism. Mm-hmm. That is when you give potentials to the radions, and then this way you stabilize the two brains. Here, it has to be massless, because it is massless in the universe. So that's your modulus. It's a modulus field in that construction.
Oh, I see. Mm-hmm. Okay.
Now, when it gets the mass at low energies, there should be some similar stabilization mechanism. So that story we have not translated back to the Randall syndrome picture.
Okay, I see. And to get in the mass, we're only assuming that you have a strongly coupled theory.
That's right, because that's the only coupling. The difference in conventional Randall syndrome is that that's the only coupling that this one has here. So,
okay, thank you.
Yeah. And it's also holographic Randall syndrome. It's on the other brain than in their case. So, yeah, Greg.
Just one second. Changi was first.
You said after the QCD transition, it becomes massive. What's your estimate of the mass of this sigma?
Yeah, so the formula is in the leading approximation. In the simplest case, if I don't assume, let's say, quartic interaction for that phi, then in the simplest case, the leading term will be this, lambda QCD square over m bar.
Okay, can you give a number?
Yes, so for that kind of m bar, this would be like 10 to the minus 4, 10 to the minus 5 EV. Yes. Way lighter than okay, that's an important question. Because this is lighter than those glue balls, that's why you have right to kind of integrate glue balls out and still keep it in your theory, as it was done as I alluded to, the essence of that paper is that you want to integrate out glue balls, but retain in your low energy theory all the information about word identities. And that's the construction, yes. Ah.
No, let's thank Greg.
What about the fermions, the Timoney of fermions? You have,
Fermions?
yeah, you have a, yeah, because there's not two derivatives, right? But the scalar field is always del.
Yeah. Yeah. Yeah, yes.
So,
it's not.
for any known, it's not.
No, only anomaly part of this.
Oh, okay. Okay.
Yeah.
Thank you.
No, otherwise, yeah.
Yeah, otherwise the mass change, everything.
Sure.
By the way, I'm Eliud San Bernardo.
Oh, okay. Nice to
I
meet you.
work with Stefan.
Yeah,
on
yeah,
the
yeah.
distiller,
That's right. Yes. Okay.
So
So
thank you
very
for-
good.
thank
No,
you for
thank you.
taking
I should read all those messages. I didn't have time to read all those messages. There was exchange, I know, and you were answering very well.
Yeah, we
But,
fight a little bit.
But that's okay. I think you are right.
Okay, I think the problem is that after the field redefinition, he's forgetting because if you have the fermion,
Yes.
I'll just write like, you can write like this.
Oh, I'm sorry.